In this video we are going to talk about the difference between complex derivatives and real derivatives. We will also see how naturally the Cauchy-Riemann equations appear in this context. So here is the goal. So given a function f that takes complex plane to itself and is differentiable, what is the difference between this and the same function viewed from R2 to itself being differentiable? Let us start with a motivation. The complex plane can be identified with R2 via this canonical map. So if we have a complex number z given by x plus iy, where x is the real part and y is the imaginary part, we can view this as an element of R2 with coordinates x and y. And vice versa. Any element of R2 with coordinates x, y can be written as a complex number x plus iy. So now with this, any function that maps z to itself can be viewed as a function from R2 to itself. Indeed, if we start with a function from z to itself that takes the point z and maps it to the point uz plus ivz, so in other words u is the real part of f and v is the imaginary part of f, then if we use this notation for the function u, so u of xy, we just identify it with u of x plus iy, then we can view f as a mapping from R2 to itself, which takes the vector xy to the vector with coordinates u and v. And conversely, if we start with a mapping from R2 to itself that takes the vector xy to the vector uv, we can view this as a mapping from C to itself that takes the complex number x plus iy to the complex number u plus iv. It is a famous result in complex analysis that if we have a function that takes c to itself and is differentiable in a neighborhood of a given point p, then it is infinitely differentiable there. So existence of one derivative implies that you can differentiate it infinitely many times. Now this is a very strong statement, which is not true for real valued function. So in particular, if we look at a function from R2 to itself given by x to the power 6/5 and 0 in the second coordinate, this function is differentiable near the point 0, 0, but the higher order derivatives don't exist at the point p. And the reason is that if we differentiate the first component, which is denoted by u, once, if we take the partial derivative with respect to x, we get 6/5 times x to the power 1/5. And this is not differentiable at the point x is equal to 0 because the second order partial derivative has negative power of x, which blows up there. So this is a stark difference between real differentiability and complex differentiability. But what do we mean by this? Because as we saw above, the function that maps c to itself is basically the same function that maps R2 to itself. It's just another way of rewriting the same function. So this is the question we're going to address in this video. What is the difference between differentiability of f from c to itself versus that of f from R2 to itself? And to answer this question, we need to recall the definition of differentiability. So let us start with the one-dimensional case. If we have a function f that maps R to itself, which is defined near the point p, then it is called differentiable at point p if and only if the following limit, so limit of f of p plus h minus f of p over h, as h approaches to 0 exists, and we denote that limit by a. Equivalently, we can take a to the other side, bring to common denominator, and obtain the following formulation. So f is differentiable if there exists a finite number a, so that this limit is equal to 0. Of course, this number a is also denoted by f prime of p and is called the derivative of f at the point p. But to be able to generalize this definition, we shall view the derivative not as a number, but rather as a linear function. For that, we introduce this new notation, df of p, which is a linear function from R to itself, so it takes the entry h and multiplies it with the number a. So it's a simple function defined by multiplication by a. The subscript p denotes the dependence of this on the point p. So in other words, the derivative is at the point p. So this linear map, or the linear function, is also called the derivative of f at the point p. It's a slight abuse of terminology, but sometimes this is also called the total derivative of f. Now, the advantage of introducing this linear function definition of the derivative is that now we can readily generalize the definition of differentiability to higher dimensions. But we are going to look at the case of functions from R2 to R2. So, if we have a function f that maps R2 to itself, which is defined near the point P, then it is called differentiable at the point P if there exists a linear map, which we will denote by df of P, which takes R2 to itself, such that the following limit is equal to 0. So, you see that the analogy between this expression and the above expression. So basically we replaced AH by df of P at H. Well, in this case we have absolute values, and there are a few remarks regarding this definition. So let's look at that next. So again, here we have the definition of differentiability. So first of all, H is a vector in R2, and the absolute values denote the length of vectors in R2. So numerator is a vector in R2, denominator is a vector in R2. Second, one can show that if such a linear map dfp exists satisfying this property, then it must be unique. In other words, this property can be used to define the derivative of a function, and it is well defined. Next, dfp is a linear map that takes R2 to itself. Hence, it must be given by a matrix multiplication. So there exists a 2x2 matrix A with real valued entries, such that dfp of H is equal to A times H, and this is a matrix multiplication. A is a 2x2 matrix, H is a two-dimensional vector. Next, another common way of rewriting 1 is the following. F of P plus H is equal to F of P plus AH plus little o of H. Well, here we see the linearization formula of f near the point P, and A is the linearization. And what is little o of h? So little o of h denotes any function r of h that satisfies this property. So limit of r of h divided by h must be equal to 0. And the way this is obtained from 1 is simply we just set the numerator inside the absolute value to be equal to r of h. Then obviously we have this property for r of h, and then if we take these two terms to the right hand side, we obtain the following representation. Another observation is h is any vector that approaches to 0 in R2. So in particular, we can let ah to approach 0 along x-axis or along y-axis. Then one can show that this equation implies that all partial derivatives exist at the point P. And moreover, if we write u and v to be the coordinates of the function f, then A is just the matrix of the partial derivatives. So the first row becomes partial x of u, partial y of u, and the second row becomes partial x of v, partial y of v, all evaluated at the point P. And sometimes for A, the gradient notation is used. All of this is a quick review of differentiability. So now let's look at the differentiability in complex plane. So again here, we just repeat the definition of differentiability of a function from R2 to itself, and next to it we put the differentiability of a complex function. So if we have a function that maps C to itself, which is defined near a point P from the complex plane, or from the complex numbers, then it is called differentiable at the point P if there exists a linear map that takes C to itself so that the same quotient limit is equal to 0. Well, now we compare these two definitions. What is the difference between the two? This is the question we're trying to address and understand. And the answer is hidden in the following piece. So for real differentiability, df of P is a linear function from R2 to itself, and for complex differentiability, dfp is a linear function from C to itself. So if we use a shorthand notation for dfp and denote it by t, then the question boils down to the following. Given a linear map T that takes R2 to itself, when is T also linear as viewed from C to itself? So we're looking at the difference between linearity on R2 and linearity on C. Well, linear functions must satisfy two properties. The first one is additivity. So t applied to a sum of two vectors can be written as sum of two vectors obtained by applying t separately. So this equation must hold for any z1 and z2 from R2. But because elements of R2 and C can be identified with each other, so the same equation is equivalent to itself written for any z1 and z2 in C. The key difference is in the second property of linearity, which is related to scalar multiplication. So t as a linear map from R2 to itself must be linear implies that t of lambda z must be equal to lambda times t of z, and here this must be true for any real number lambda and any vector z in R2. So this is the scalar multiplication on R2. On the contrary, if we have t that is linear from C to itself, then this property must hold for any complex number c and any z in the complex plane. So we see that this is the stark difference between the two. So the first property must hold for all reals, and the second one must hold for all complex numbers. So in particular, this is a stronger statement. We require more. So we require this identity to hold for all complex numbers. And this is the reason, we'll see later, that complex differentiability is a stronger statement. It requires more than real differentiability. So if we go back to view T as linear maps, this is what's happening. So R2 is a vector space, and so is C. So in the first property, we have scalar multiplication by elements from R. So in particular, we look R2 as a vector space with the scalar field R, whereas we look at C as a vector space with the scalar field C. So this is the key difference. Okay, so if we start from a map T that is linear from R2 to itself, then we know it is given by a matrix multiplication. So T takes the vector xy and multiplies it with the matrix A. And if we write A, B, C, D to be the components of the matrix A, then this is how we obtain the representation of T. The first component is AX plus BY, obtained by multiplying the first row with the column vector XY, and the second component, second row of the matrix, multiplied with the column XY. Now, viewing this map as a map from C to itself means the following. So, XY vector corresponds to the complex number x plus IY, and this outcome vector corresponds to the complex number AX plus BY as the real part, plus I times the second component, CX plus DY, as the imaginary part. Now we're interested in understanding when such a map is linear from C to itself. The only thing that we are missing is multiplication with the purely imaginary unit. So if we can pull out I from multiplication, then combined with the first property, we can tell that we can pull out multiplication by any complex number. So let us look at multiplication by the complex unit I and see what kind of information does that give about T. Okay, so if we look at T of IZ, well, first of all, we're multiplying Z by I, so I times X plus IY, so the real part becomes I square Y, which is negative Y, and the imaginary part becomes IX. So if we look at the definition of T, X is replaced by negative Y, and Y is replaced by X. So then this is the outcome. Minus IY plus BX plus I times minus CY plus DX. On the other hand, if we look at I times T of Z, so we take the right hand side here and multiply it with I. Again, using that I square is negative 1, the real part is minus CX minus DY, and then plus I times AX plus BY. Now these two expressions must be equal to each other, which means that the real parts must be equal and the imaginary parts must be equal. So then we obtain these two equations. Now this must be true for any xy in R. So in particular, let's say we can set x is equal to 0 and take y is equal to 1 to conclude that A must be equal to D. Similarly, we can let y to be 0 and x to be 1 to conclude that b must be equal to negative c. And the second equation gives the same information. So this is the equivalent formulation of the system. C must be equal to negative b and d must be equal to a. So now if we go back to the definition of t and then substitute these values, so we replace c by negative b and we replace d by a, this is the expression we obtain. And now we can factor out x from this term and that term and obtain a minus ib times x. Similarly, we can factor out I times y from this term and from that term. And again, we have I times a minus ib times y. Now we can pull out a minus ib from these two terms, and the result reads as a minus ib times x plus iy. And we obtain something very familiar and not surprising at all. Linear function from C to itself must be given by a multiplication with a complex number. And indeed, t of x plus iy is equal to some complex number times x plus iy. Or equivalently, if we go back to the matrix notation, we obtain the following. So the matrix of T must have this form. So the diagonal elements must be equal to each other and the off-diagonal elements must be opposite to each other. So combining all of this, we proved the following lemma. If we have a map T from R2 to itself that is linear, and its matrix is A, B, C, D, then the following are equivalent. T from C to itself is a linear map, and the diagonal terms are equal to each other, and the off-diagonal terms are negative of each other. But if we go back and recall what we started with T from the derivative matrix, and A was the matrix of partial derivatives, well, all of which evaluated at p. And here, the coordinates of f are u and v. So then C linearity condition, so this condition over here, written for this matrix A, is just following system. Partial x of u is equal to partial y of v, and partial y of u is equal to negative partial x of v at the point P. But we recognize these as the famous Cauchy-Riemann equations. So we see how Cauchy-Riemann equations appear here as simply linearity of the derivative, as a map from C to itself. And the conclusion is the following theorem. If we have a function f from R2 to itself defined near the point P, then the following are equivalent. F is complex differentiable at the point P, and f is real differentiable at the point P, plus the Cauchy-Riemann equations hold. So we see that complex differentiability is more than real differentiability, so it asks for this extra two conditions to hold at the point P, which are partial differential equations. So hopefully this sheds some light into the difference between real and complex differentiability.